then we're finding the exact equation. The whole thing that we're doing is plugging in what we know and solving for what we don't. So in these, we are given an HK. We're given a locator point, the type of equation. So this particular one in the example is a hyperbola. And then we're given what's called a passing through point, or just any point on the graph. So our general equation for that family, for the hyperbola, remember that's also called a rational. That's what it is on your toolkit. Is y equals a times 1 over x minus h. You can also put the a on the top there if you want to. I find it easier to solve this way, but whatever you want to do is fine. And then plus k. And then you determine what you know. If I have a locator point at 2, 3, then I know I have an h that equals 2 and a k that equals 3. I also know that it passes through the point 5, 4, which means somewhere in on that graph, I'm going to pass through that point, which means that's an x value for 5 and a y value for 4. So I plug in everything that I know. So fill in the locator point. We'll leave this as a partial equation. I wouldn't necessarily use this step every time, but we're going to do that right now. So y equals a times 1 over x minus 2 instead of h, and then plus 3 instead of k. And I don't like the amount of space in here for showing the work, but I'm going to do a couple columns probably. So then now I'm going to plug in my x and y as well. So instead of y, I have 4. So actually, I'm going to show you what this looks like from the beginning. If you do this part, I would write it lightly. So I have my general equation. So that's my general equation. I know that y equals 4. So I'm going to take out the y and put 4. I know that x equals 5. So I'm going to take out the x. Put in 5. I know h equals 2. Take out the h and put in 2. Be very careful with your negatives on those if you have a negative h. And then I'm going to take out the k and put in 3. So now I have my equation all done here, and the only unknown I have is a. So now what I'm going to do is simplify what I can and then solve. So the first thing I'm going to do is simplify the denominator here. So 5 minus 2 gives me 3. So 4 equals a times 1/3 plus 3. Remember that you're multiplying these two, so in the order of operations, you multiply and divide before you add and subtract, and then when you're solving, you go backwards with that. So you need to get rid of that plus 3 by subtracting 3 from both sides. So I have 1 equals a times 1/3. So a couple ways of looking at this. If I'm multiplying a times 1/3, I can divide by 1/3, or when you're multiplying by a fraction and you want to get rid of it, you can multiply by the reciprocal. I mean, that's mathematically what we're doing when we divide. So we can multiply this by 3 over 1 on both sides. So that divides out to 1, so I'm left with a. 3 over 1 times 1 is just what? 3. 3 times 1 is 1, divided by 1, or sorry, 3 times 1 is 3, divided by 1 is just 3. So a equals 3. So when I write this whole equation, give everybody a second to catch up there. write this whole equation out, it's going to be y equals 3 times 1 over x minus, and then I want to write in my h and my k. So x minus 2, then plus 3. You can also put this 3 up here if you prefer. Whichever makes sense to you is fine. So after in the previous examples we've done, after I told you that I wasn't going to have basically a stretch factor for the graph, I am giving you an example like that. So I'm going to show you kind of how that would work. If we look at a normal hyperbola, well, let's go ahead and graph our asymptotes first. So we're going to have an asymptote at 2 and 3. So we'll have a vertical asymptote at 2. Do that in the highlighter. And always do your asymptotes in dashed lines. And then one at positive 3. So normally, when I put in this point right here and this point right here, these two diagonal points with a regular hyperbola, that's because if I have y equals 1 over x, and I put 1 in for x, then I'm going to get 1 for y. If I put negative 1 in for x, then I'm going to get negative 1 in for y. So in this particular case, if I have 3 times 1 over x, and I put 1 in for x, and pretend for a moment that I have taken the origin and moved it up, because that's really what I'm doing when I do this. If I put 1 in for x, and I multiply it by 3, then I'm going to go up 3. And in the other direction, if I want, well, I don't even worry about the other direction. What you need to know about a hyperbola is that they are symmetrical along a diagonal line. So any point that I have over here is also going to be over here. So, and on that same note, it's going to be in the opposite quadrant as well. That is confusing, and I know that's confusing, which is why I'm generally not going to test you on something like that with the hyperbola. But just know it's the general shape that's important. And that's supposed to go down next to the asymptote, not hitting it. And the real takeaway that I want you to get from this is not that the graph of it as much as how to find A, because that's what we're really taking the notes on. We also know that we have a passing through point, sorry, that's the other thing, of 5, 4, which can help us as well. This is that 5, 4. So that can also help us build the rest of it, because we know we have reflections on different parts of that. Questions on that one? So, example 2, we have a parabola. And we know that general equation is y equals a times x minus h squared plus k. Parabola is also called the quadratic. So a partial equation with h and k substituted in. Y equals a times x minus 12 squared plus 9. So then I'd plug in my x and y for my passing through point. So we have a y of 49 and an x of 2. And then drop down the rest of it. So then we simplify what we can before we start to solve. So 2 minus 12 is negative 10. So 49 equals A times negative 10 squared. Don't forget to bring down the squared. It's a very important part. Plus 9. Subtract 9 from both sides. So we have 40 equals A times, and I'm going to go ahead and square that. Negative 10 squared is going to be positive 100. Make sure you recognize that anything squared will always be positive. And then I'm going to divide by 100. And I prefer to leave things in the fraction form. So those zeros divide out, so I'm left with 4 over 10, which reduces to A equals 2/5. So my final equation, y equals 2/5 x minus 12 squared plus 9. Now, I've of course given you another example that's a little tricky to graph, mostly because this doesn't fit on our graph. So if I look at this in terms of my locator point, let's go ahead and scribble out those 5s. I'm going to treat this one as though each of them were worth 2. So I'm going to first graph my locator point at 12, 9, so I'm going to be right there. And because that A is 2/5, is that graph going to be wider or skinnier than a normal one? Wider. The fraction between 0 and 1, or 0 and negative 1, remember, makes it wider. So the whole number is going to make it skinnier. So I'm not going to worry too much about the details, but it's going to go out more than a typical parabola would. And that's the point that I want you to get, is not so much the details of the graphing today as how to solve for A and how to place that on your graph more carefully. We can do the more careful stuff, later.